So before we begin this video, I want to issue a quick correction. So throughout this video, I actually used the incorrect gas constant. So the universal gas constant is actually this number, 0.08206. Throughout the video, I'm going to use this value 0.08314. This is incorrect, right? So make sure you correct your notes, or if you're taking notes, or if you're just watching the video, make sure you note that this is the correct value of the gas constant, not the value that I'm going to use in this video. This 0.08206 is the correct value for the gas constant. With that correction, let's move on to the video. In this video, we're going to discuss gas stoichiometry. And basically, this is just a class of problems that utilize the ideal gas law or results from the ideal gas law to help solve problems in stoichiometry. Now, before we look at a specific example of this type of problem, I want to introduce something called standard temperature and pressure. So standard temperature and pressure. And this is usually abbreviated as STP. So standard temperature and pressure, or STP. So basically, standard temperature and pressure is 1 atm as our standard pressure, and the temperature, the standard temperature, is 273.15 Kelvin, or 0 degrees Celsius, right? So this is our standard temperature and pressure. Now, if we look at the ideal gas law, we can actually get a more or less a conversion factor for what volume 1 mole of gas is going to occupy. And this was implicit in the video on Avogadro's law, but I'm going to make sure it's explicit here. So let's look at the ideal gas law. Right, so we have PV equals nRT, right? And let's say we want to calculate the volume of 1 mole of gas at standard temperature and pressure, right? So we know we'll have to isolate the volume here. So we'll have nRT over P, right? Then we just have to plug everything in order to solve, right? So we get volume is equal to 1 mole, our gas constant, 0.08314 liter ATM per mole per Kelvin, right? 273.15 Kelvin as our standard temperature over the pressure, which is 1 atm. And so when you do that calculation, you get that the volume should be equal to 22.42 liters, right? So this is the volume that 1 mole of gas will occupy. So we know that at standard temperature and pressure, we can make the following claim, that 1 mole is going to be equal to 22.42 liters. Right, so this is true at standard temperature and pressure, that 1 mole of gas is going to occupy 22.42 liters. And so we can utilize that when trying to solve problems of stoichiometry if we know the volume and or the number of moles, right? So let's look at an example and see how we will put this to work. So the problem says, consider the following reactions. So we have aluminum reacting with oxygen to form aluminum oxide. And it says it takes 2 liters of pure oxygen gas at STP, standard temperature and pressure, to react completely with a certain sample of aluminum. What is the mass of aluminum reacted? Right? So we've been given information about our gas sample, but we've been given the volume, right? But since we know the ideal gas law, we know that if we have the volume and we know it's at standard temperature and pressure, we can actually solve for the number of moles. And then from there, we just treat this like a standard stoichiometry problem, right? So we've been given, right? We've been given the volume, right? The volume is 2 liters. And we've been given STP, right? So we know that the pressure is 1 atm and the temperature is 0.15 Kelvin. So believe it or not, from just this information, we can actually answer the question that's been asked. So first, let's figure out how many moles are in 2 liters of oxygen gas, right? So if we have 2 liters of oxygen gas, from what we saw previously, we know that at standard temperature and pressure, 1 mole of gas is going to occupy 22 liters. So we can plug that in here. So every 1 mole of gas will occupy 22.42 liters, right? So your liters are going to cancel out here, right? So you're left with moles. So that means that in this 2 liter volume, we have 0.089 moles of oxygen gas, right? Now that we have the number of moles of oxygen, we can use that and just solve it like we would any other stoichiometry problem. We know that 0.089 moles of oxygen is reacting here. So we can solve this problem. So it says what a mass of aluminum is reacted. So that's a relationship between the 2 reactants. So we'll use the mole to mole ratio between those 2 in order to solve this. So we got 0.089 moles of O2 based on the stoichiometric ratio from the balanced chemical equation. We know that for every 3 moles of O2, we have 4 moles of aluminum, or we react 4 moles of aluminum. All right, so that means that we're going to react 0.119 moles of aluminum. And it's specifically asking us for a mass here. So we have to take this number of moles and convert it to a mass. So doing that, we have 0.119 moles of aluminum. The molar mass for aluminum is 26.98 grams of aluminum for every 1 mole of aluminum. And that's going to give you a final mass of 3.21 grams of aluminum. Right? So think about what we were able to do here. Just being given the volume of oxygen gas that's going to react, we're able to calculate how much aluminum is reacted in this equation, right? Kind of putting together our powerful ideal gas law with everything we know about stoichiometry to be able to solve a question like this, right? So this really puts both of those skills to use, kind of marrying both skills to be able to solve these types of problems of stoichiometry involving gases.